Onward to more problems. We can do this. So, what do I have here? Well, for this one, I'm going to need a picture. We've got an automobile tire. Oh my goodness, look at this beautiful artwork. I'll draw it in two places because it's going to be changing. So, this is the gauge pressure. That's a key word here. Of an automobile tire is measured to be 200 kilopascals before a trip, and it's 220 kilopascals after a trip. Okay. And atmospheric pressure for both of these is 85 kilopascals. This is assuming the volume of the tire remains constant at 0.035 meters cubed. Determine the percent increase in the absolute temperature of the air in the tire. Great, but what's the temperature? Doesn't give it to us, does it? Now, we totally could calculate the temperature. That would be 100% fine. However, we might have some other ways of doing this. So let's write down what we know. First off, we know that air is an ideal gas, right? Okay. Now, since air is an ideal gas, that means we can use the ideal gas equation. The whole, PV equals nRT thing. I'm going to use the one I like best, which is P lowercase v is equal to RT. Now we know the volume is the same for both. So if I solve for volume here, what I get is that V is equal to RT over P. Okay, and so this should be the same for both. So RT1P1 should be equal to RT2 over P2. Like, Dr. Kidd, where are you going with this? You'll see in a second. You'll see in a second. So if I cancel the R's, because they're both there, I can then rearrange this a little bit. And what I then get is that T2 over T1 is equal to P2 over P1. And this right here can give me the percent difference without knowing either of the temperatures. I don't actually have to know them to be able to calculate this. So let's find our pressures. As a note, that is not P2. Why? Because this is gauge pressure. We need the absolute pressure. Remember, this is the ideal gas law, always absolute pressure too. Well, how do I get absolute pressure? It's not hard. We had this equation all the way back in chapter 1. So P absolute is equal to my atmospheric pressure plus the gauge pressure. Remember, gauge is simply saying how far above absolute pressure are you. And so if I do that for this first one, I get 285 kilopascals. If I do it for the second one, I get that's equal to absolute pressure. That's equal to 305 kilopascals. So then I can plug that in here. So I see that T2 over T1 is equal to 305 over 285. Let's see what that is in the calculator. 305 divided by 285. And it is equal to 1.07017. Okay. Now, if you're trying to figure out what the percent difference is, just subtract 1 from this and then multiply by 100%. The 1 is simply saying that, it's not, changing by that much. It's because this is how the ratio. If I subtract 1, I'll get the difference there. You're like, well, how do you know that, Dr. Kidd? Because this is the percent difference formula. It's equal to delta T over your original temperature times 100%. And so, how do I make my equation from there? Well, T2 over T1 minus 1, which is the same as T1 over T1, times 100%. And so if I gulp that together, guess what? They all come out there. Same equation, works out just fine. And so what do I get from this? Let's see. It's going to be equal to 7.017%. And we never even had to use that volume or calculated temperature. Isn't it nice when math works? I like it. Hopefully you like it too. Okay, that's it for this problem. Thanks so much. See you later. Bye-bye.